Dear friends, once again I would like to welcome the last part of the chapter Stereochemistry of Disubstituted Cyclohexane. That's part 3. Myself Dr. T.B. Pawar, LVH Arts, Science and Commerce College, Panchoti, Nasik. In this chapter, we are going to discuss 1,3 and 1,4 disubstituted cyclohexane. Let us start with the slide 1,3 disubstituted cyclohexane. It exists in two forms, cis and trans form. That means there are two geometrical isomers, cis and trans. First of all, we are going to explain the cis isomer. The cis isomer, the methyl groups are either axial or equatorial position. Here at C1CS3 axial position, at carbon number 3 CCS3 axial position. Both the methyl on the cyclohexane at 1,3 position are on same side of the general plane, so it is a cis isomer. Now here the structure 1, when structure 1 flips into structure 2, the methyl group at carbon number 1 is an axial position in a structure 1. When flips to 2, it changes to equatorial position. Same, the CH3 at carbon number 3 in the structure 1, axial, it changes to equatorial position. So this structure becomes a equatorial 1,3 dimethyl cyclohexane, that is cis, because both the methyl groups are projected upward direction. Both the methyl groups are on the same side of the general plane, so it is a cis structure. Now if we place a mirror between the molecules, the mirror image of 1 becomes a structure 3 and mirror image of 2 becomes a structure 4, and these are the superimposable mirror image. Now we can explain this cis isomer by using the two major points, optical isomerism and relative stability. First, optical isomerism. So the cis 1,3 dimethyl cyclohexane, here suppose we draw the 4 different structures, axial, equatorial. Optical isomerism, this point is concerned with the any type of symmetry, any elemental symmetry. Here if we pass the plane between carbon number 2 and 5, then the molecule is exactly divided into equal halves. The molecule is divided into equal halves. Means this part of the molecule having a particular optical activity is exactly cancelled by optical activity of this part. Means the molecule becomes a meso molecule, and so the molecule is optically inactive. Similarly, an equatorial position, whenever the plane passing through C2, C5, then it shows again a plane of symmetry and the molecule becomes a meso compound here. And meso compounds are optically inactive. Now again we have seen the conformation 1 and 3 and similar 2 and 4 are superimposable images. Now the relative stability of this 1,3 dimethyl cyclohexane. The stability we can compare by using the energies. Now here each is CS3, here this axial CS3 and axial CS3 at 1/3 position. So, and that is at carbon number 5 one axial hydrogen, CS3 at axial hydrogen at 3rd position. There is 1,3 diaxial interaction, 1, 2, 3, 1, 2, 3. So 1,3 diaxial interactions are Gauss interactions. See carbon number 1, at carbon number 1 there is C1CS3 is gauge to the carbon number 3, C1CH3 is gauge to the carbon number 5. Similarly, at carbon number 3, that CH3, CCH3 is gauge to the carbon number 1 and CCH3 is gauge to the carbon number 5. So there are each axial methyl group has 2 gauge interactions or 2 1,3 diaxial interactions. Total becomes 4 gauge interactions or 4 diaxial interactions, and the energy of these 4 gauge interactions are 3.6 kilocalorie. This one interaction, this one interaction, this CH3, this one interaction, this one interaction. But in addition of these two, there are these 2 bulkier methyl groups are gouged to each other. Strong interactions, and so in addition to this, there is 1.8 kilocalorie per mole energy steric interaction mole. So we can add 3.6 plus 1.8, it becomes 5.4 kilocalorie per mole energy. So it is highly unstable as compared to other isomers because of both the methyl groups are bulkier methyl groups are axial and 1/3 position. Now, equatorial 1,3 dimethyl cyclohexane. Here there is no any interactions because both the methyl groups are extended outside the ring, so no any interactions, and so the energy is 0 kilocalorie per mole. It's a very stable isomer. Now, trans 1,3 dimethyl cyclohexane. In the trans 1,3 dimethyl cyclohexane, both the methyl groups are in the opposite side of the general plane. So it is a trans. So it may be axial equatorial position or equatorial axial position. After flipping structure 1, there is formation of this CCH3 changes to axial, changes to equatorial. This equatorial changes to axial, and here these two are also opposition, one posited above the plane, another below the plane, so trans. Now if you place the mirror, then the mirror image of 1, 3 and the mirror image to structure 4, structure 3 flips into structure 4. These two are the enantiomers of one another, these two are the enantiomers of one another, and all they have equal energy. Now we are going to discuss by using the optical isomerism and relative stability. First of all, optical isomerism. The trans 1,3 dimethyl cyclohexane has no plane of symmetry. If we pass the plane through this, there is no plane of symmetry. So the molecule is optically active. Now here we have seen conformation 1, 3 and similarly 2 and 4 are the non-superimposed molecules. That means they are the enantiomer 1, 3 and 2 and 4 are enantiomers of one another. Now when structure 1 flips into structure 2, both 1 flips into 2, both are identical. They are superimposable, that is, they are identical. Similarly, structure 3 and structure 4 are identical, and hence they have equal stability. Now, the relative stability of trans 1,3 dimethyl cyclohexane. Here, this C1CH3 is gouged to the carbon number 3, C1CH3 is gouged to the carbon number 5. Or C1CH3 axial CH3 is 1,3 diaxial interaction between from this 1 to 3, 1 to 3. Two 1,3 diaxial interactions are there, and each 1,3 diaxial interaction we know 0.9 kilocalorie per mole. So total becomes energy of the molecule becomes 1.8 kilocalorie per mole. Now the stability of equatorial form. This 1,3-dimethyl cyclohexane, both the methyl groups are in an equatorial position, and there is no, both methyl groups are extended outside of the ring, and that's why there is no any type of interaction. So it is a very stable one, and the energy of this molecule is 0 kilocalorie per mole. Again, we have seen the stability of this whenever one is axial, then 1.8 kilocalorie per mole, axial equatorial form, or equatorial form 1.8 kilocalorie. And whenever both the methyl groups are in an axial position, it's highly it's less stable than other isomers, because strong steric interaction, 1,3-diaxial interaction, and bulkier methyl group interaction in 1/3 position, the energy is 5.4 kilocalorie per mole. So the cis 1,3-dimethyl cyclohexane equatorial form is the highest stability, more stable than the trans 1,3-dimethyl cyclohexane, whenever the equatorial axial or axial equatorial position, and this is more stable than the axial form. Now the last one is 1,4-dimethyl cyclohexane. 1,4-dimethyl cyclohexane, whenever both the methyl groups are projected in upward direction or on the same side, so it is a cis isomer. Now structure 1 flips into structure 2. Here axial methyl changes to equatorial, and equatorial methyl changes to axial when placed. We place a mirror, then the structure 3 is mirror image of structure 1, and 3 flips into structure 4. Structure 4 is a mirror image of structure 2. Again, we are going to discuss by using the optical activity and relative stability of the isomer. First of all, optical isomerism. Again, here if we pass the plane through C1 and C4, then molecule shows a symmetry, plane of symmetry here, and because of plane of symmetry, the molecule shows a meso compound, and the meso compound is the optically inactive. The conformation 1, 2 and 3, 4 are superimposable, hence optically inactive. Now relative stability. Here one of the methyl is in an axial position, so it shows the 2 1,3-diaxial interactions or 2 Gauss interactions, and each Gauss interaction 0.9 multiplied by 2, so 1.8 kilocalorie per mole. Now 1,4-dimethyl trans isomer. Here the trans isomer is a very interesting example. Trans isomer, both are equatorial or both are axial. Both methyl groups are equatorial or both methyl groups are axial. So here the structure 1 when flips into structure 2, equatorial changes to axial, and both are in opposite side of the general plane, so it is a trans one. If we place the mirror again, then structure 1 is the mirror image of structure 3, and structure 4 is a mirror image of structure 2. Now again the optical isomerism. Yes, if we pass the plane between C1 and C4, the molecule divided into 2 equal halves, so plane of symmetry is there. Again here from C1 to C4, plane of symmetry. Along with plane of symmetry, there is center of symmetry is also there here. And that's why, because of plane of symmetry and center of symmetry, the molecule is optically inactive. Now relative stability of trans. Whenever both methyl groups are in axial position, that means there is a strong interaction, and because of interaction, energy of the molecule increases and the molecule becomes less stable. So 1,4-dimethyl cyclohexane, whenever trans-axial form, it is less stable than its equatorial form. Energy here, this 1,3-diaxial interaction Again this 1,3 diaxial interaction. This CH3 shows a 1,3 diaxial interaction with this hydrogen, 0.9 kilocalorie per mole. Again this shows a this axial hydrogen, 0.9 kilocalorie per mole. Total energy becomes 0.9 multiplied by 4, that is 3.6 kilocalorie per mole. Here both the axial methyl groups are Gauss 2 at the carbon number third carbon. That means the carbon number 1 is Gauss to the carbon number 3. Carbon number 1, the CH3 axial, CH3 is Gauss to the carbon number 3, C1CH3 is Gauss to the carbon number 5. That is in these two 1,3 diaxial interactions. Similarly, the carbon number 4, the CH3 is Gauss to the carbon number 2 and Gauss to the carbon number 6. So these are two 1,3 diaxial interactions. Total 4 Gauss 1,3 diaxial interaction. So 0.9 multiplied by 4, 3.6 kilocalorie per mole energy of the molecule. Now whenever the equatorial is there, here there are again no any interactions, so it is very stable and the energy is 0.0 kilocalorie per mole. Now the stability order of all these cis and trans isomers of 1,1,4 dimethyl cyclohexane, whenever the equatorial it's highly stable and the energy is 0 kilocalorie per mole. And whenever the cis form, means one having axial and another having equatorial or equatorial axial, then the energy is 2 Gauss interaction, 0.9 multiplied by 2, 1.8 kilocalorie per mole, and the last one, that is trans 1,4 dimethyl cyclohexane, but the methyl groups are in a axial position. Each axial methyl group shows 2 Gauss interaction. Total becomes 4 Gauss interaction. 4 multiplied by 0.9, 3.6 kilocalorie per mole. So it is a least stable than all other isomers. So the stability order, here we have finished the chapter. Thank you.